Hello. We'll wait for 5 minutes and after which we will stop. Hello. Rajani, is it audible?
Hello? Yes, sir, I can hear you.
Okay.
Yeah.
Hello.
Hello? Sir.
Yeah. Good evening, everyone.
Yeah, we can hear you, sir. It's clear.
Hearing- Yeah, Niru, you can turn off your camera if you want to. So fine. So this is a lecture two of our electrical machines, and we'll discuss some kind of problem so that it will help you in assignment two. And my name is Abhishek Munshi, and I'm a Pmrf research scholar at IIT. I'm working at Transportation Electrification Lab. This is the YouTube link, which I'm also shared in the comment box so that you can go there and see the previous videos if you require. And this is the drive link where you can find the PPT of the last video also. Uh, and I will upload this PPT also there so that it will help you all. Fine. So basic agenda of today's lecture is to basically the um, equivalent circuit of a transformer. I will discuss in the last class, and today I will show you the equivalent circuit of the transformer, and we'll see the components over there, and after which we'll discuss a little bit about the losses, and we'll solve some problem regarding that. So while doing the lecture, try to put the formulas in your copy so that you can able to solve it by yourself. So I will give 2, 3 minutes, 5 minutes for per question so that you can able to solve and be in the class. Okay. So first topic we're discussing today is the no load equivalent circuit of a transformer. So if you see in the last class, I also discussed about the transformer. You already know that the basic circuit of a transformer. And if we do the equivalent transformer circuit, it will look like this. Okay. So this section, basically, this parallel section R naught XM, it will gives the equivalent of the core of the transformer. So if you remember that this is basically a transformer, right? Basically, this is a transformer, this is the primary side, this is the secondary side, and this is the core of the transformer. So if you do the equivalent circuit of that in terms of resistance and reactance, then this should be the core of this transformer. The core should be this. And this is the primary and secondary side, and on which this is the EMF developed on the primary side and the EMF developed on the secondary side. There is a voltage across the secondary while there is no load. So we have R1, X1, these are the primary resistance and the primary reactance. Can also represent it by RPXP, if you require. And I1, this is basically the primary current flowing through the circuit. This is I2, which will be induced over there in the secondary side, and ultimately we'll get a secondary EMF E2 over there. Fine. And this is the core component we already showed there in the this block diagram. Fine. And this one is the secondary resistance, and this one is the secondary reactance. Fine. So this is basically the equivalent circuit diagram of a transformer. And in case of the no load, we consider that I naught is a no load current will flow through the transformer circuit. Fine. And if you see here that basically if you apply KCL over here, then you can see that this this no load current is nothing but the I1 plus I2. And if you consider it in terms of the core loss current and the magnetizing current, then you can write it in this way that this basically the phasor sum of I naught square plus Im square from this diagram you can see. Fine. So this is basically the magnetizing component of the current I naught, and this is the non-magnetizing component. This is basically due to the core loss component and another loss we can found in the transformer. There are basically two losses. One is core loss. That loss is developed in the core, and also there will be some kind of loss when current will flow through R and X, that I square or I square X type of I square losses. That is the copper loss. Fine. So if you consider both of these components current, then you can see the phasor sum of that will be the no load current. Fine. So the magnetizing reactance, another one is the core loss. Now, I also discussed in the last class that this is the equivalent circuit diagram of transformer referred to the primary side. So while solving the problem, it is not possible for us to solve it while keeping a secondary and primary winding in between, right? So for that reason, we either have to refer it in the primary side or we have to refer it in the secondary side. And this will be the equivalent circuit of the primary side. Primary side, whenever we are referring the secondary resistance, this is R2. In I'm trying to throughout my lecture represent one as the primary and two as the secondary. Okay. So whenever we are referring the secondary resistance and the reactance in the primary side, we just represent it with R2 dash and X2 dash. Okay. So what is R2 dash and X2 dash will be, right? So for that reason, we have to know that there will be number of turns like N1 and N2. Okay. So last class I discussed that the turns ratio A or K can be noted by anything that is N1 by N2. Okay. So basically, when we are referring a secondary resistance and reactance in the primary side, it will just divide it through the square of the turns ratio. The reactance becomes like this. So this will be the R2 dash, and this will be the X2 dash. Fine. So ultimately, on the primary side, if you see from the primary side, then the total resistance of the primary side should be R1 plus R2 dash, and the total reactance at the secondary primary side will be X1 plus X2 dash. Okay. So since we are referring it in here, so minus J component, so that's why you can also write it as X1 minus X2. Okay. So basically, this is a sum. Phasor sum X1 plus X2. From the phasor, we can see that this is in the reverse side, so it will be negative. We can basically in the circuit we have to add it, but do the complex solving, complex number equation solving, then you can see that it will be minus J of component. Basically, the current is whenever you're getting the current or resistance, a basic impedance will be like R plus JX. Fine. So for the introduction of the J imaginary term, so it's putting a minus over it. Similarly, if we're referring the primary resistance on the secondary side, we can represent it as R1 dash and this as X1 dash. Okay. So R1 dash, in this case, we have to multiply it with the turns ratio square. Okay. So here also you can see that the total resistance will be R2 plus R1 dash. Total impedance will be X2 plus X1 dash. So we can represent it as the equivalent resistance and the equivalent reactance. And if you have to calculate the equivalent impedance, then you have to do the phasor sum of this. Okay. So I also discussed this in the last class in a shorter way, so I'm explaining it with the diagram this time. So this is basically the equivalent circuit diagram of a transformer whenever referring it into the primary and the secondary side. Okay. So we can also simplify it. Sorry. I'm getting hang. Sorry. So you can also simplify all of these into a approximate equivalent circuit. In case of approximate equivalent circuit, we just put the equivalent resistance and the equivalent reactance. And here we are giving the primary side voltage. This is the secondary side voltage we are getting. Fine. So in throughout the circuit, I2 is flowing. Fine. So this is basically the approximate equivalent circuit. In some cases, you can also solve it with approximate equivalent circuit. It will be more easier to solve whenever all the data are not given. We don't require to move into more into the transformer basic parameters. Then we can also solve it through the approximate equivalent circuit. Fine. One more thing that in case of a transformer, we have a basic mistake in concept that if this is my primary side and this is my secondary side, we always consider that this will be our high voltage side and this will be our low voltage side. So this is very wrong concept. Okay. So what happens? It may be low voltage side, it may be a high voltage side. Okay. So if we are uh, converting a high voltage into a low voltage, we call it a step down transformer. And if you're converting a LV into HV, then we call it as step up transformer. Based on the application, we require that whether we have to choose the step down or step up. In some cases, it happens that it doesn't require step up or step down. Okay. On that case, we basically see that if we have suppose 100 volt, we are getting 100 volt at the secondary also. This type of transformer are called isolation transformer. Fine. So in the question, we have to see carefully that whether my primary side voltage is greater or whether my secondary side voltage is greater, based on which we have to understand that which one is the high voltage side and which one is the low voltage side, not by when minimizing in your brain like that primary side will be always high voltage side. Okay. So we'll solve some problems. So this is the first problem for which we have data like a transformer of 50 hertz with a 500 turns primary and 250 turns secondary. And it has a 25 kVA rating. The rated LV voltage is 400 volt. Okay, so you have to calculate the rated primary voltage. So here it is mentioned that the rated LV voltage is 400 volts, and we from the turns ratio we can see that the primary should be the high voltage side. So fine. So it is clear from the question that the LV side is here is the secondary side, not the primary side. So don't memorize that always the primary side should be the high voltage side. So try to solve this question. This is a very basic question with the fundamental equations I discussed in the last class and this class. I'm giving 2-3 minutes to solve it, and after which I will solve it for you. Okay. And try to participate and answer in the comment box. fine. Uh, so we have to solve it. So this is basically we have LV side data like we know that VP by VS is equal to NP by NS. So basically VP is equal to VS into NP by NS, right? So VS, consider it as the LV side, is 500 by 250. So it is 800 volt. So those who are getting 800 volt is absolutely correct. Okay. So now the second question is calculate the primary side current. Okay.
Hello, sir.
Yes.
Sir, 31.25 amperes.
Yeah, I saw it. Don't say it. Fine, to solve the current, we already calculated that our voltage is 800 volt. Fine. And we have kVA of 25. This is our power over there, from which we can see that IP is basically Vp into IP is kVA, and so can write that kVA rating by our voltage Vp. So it is 25 kVA volt ampere by 800. So if you calculate it, it will be around 31.25 ampere. So those were getting 31.25 is correct, right? Now the next part is to calculate the secondary current. Right? Calculate the secondary current. Uh, putting this data because it's a common data for all the questions, right? So putting it here. So I have to calculate the secondary current IS. And we've already calculated IP as 31.25 amps. VP we calculated as 800 volt. So through this data, try to solve it. It is also very easy. I'm giving 2 minutes. Yeah, Manushami, you're saying that you can unmute and say what is your doubt, then it will be clear. Hello,
So
can
can
you
you
explain?
explain again, sir? Second question.
Second question. See,
Yes,
basically power, kVA is power, right? The kilovolt ampere, that is volt into ampere, right? So if you have to calculate the current ampere, then it should be divided by a V. So this kVA is the input transformer rating, so it should be equal to VPI, right? So if VPIP is 25 kVA, then what should be IP? Then IP will be 25 kVA by VP. Fine. So we calculated VP in question number 1 as 800. So put it over there and calculate it. Is it clear?
yes, sir. Thank you, sir.
Okay. See, here you have to calculate the IS. So the last lecture also I mentioned that IP by IS is 1 by K. Basically, that is NS by NP. Why we have to maintain the always IP NP is equal to IS NS. Fine. So here we have to calculate IS. So it should be IP NP by NS. So IP is given as we calculated 31.25 into NP is 500. This is 250. So this is 2. If you multiply it, then it will be 62.5 amp. Okay. So those who are getting 62.5 is correct. Okay. Next part of the question is we have to calculate the primary current when our secondary draws a load of 16 kilowatt at 0.8 power factor. So try to solve it. Okay. Those who are getting correct answers are Rajani, Ritish. Good. Go through the lectures for the week and then come to solve the questions and previous assignment. Then it will be easier for you all. Okay. I'm trying to give the formulas and whatever the concept you require so that you can able to solve the assignment for this week. Okay. Try to solve this one. fine. Uh, to solve this question, we have to know the basic of the power triangle. Right. So basically, we have two kind of power. One is active power, or we can often say it like real power. Okay. This is in kilowatt. Another one is reactive power, basically the imaginary power from the circuit. This is kVAR. Okay. If you go through the power triangle, then you can see that this is kilowatt, that is the active power. This is kVAR, that is the reactive power. And a phasor sum of 8 will give the kVA. Fine. And this is the power factor angle. This is basically the phase angle, or you can say it as power factor angle. So in this case, we have to calculate the primary current. So the real power draws by the secondary side through the primary side is 16 kilowatt. So this real power, active power, can be also defined as VI cos theta, where cos phi is the power factor, and this can be represented as VI sin phi, sin theta, where theta is the power factor angle. Okay. So basically, Vp Ip cos phi is given as 16 kilowatt, and we have to calculate what Ip. So we calculated Vp as 800, so it will be 16 kilowatt by 800 into 0.8. Right. So 16 10 to the power 3 by 800 into 0.8. If we calculate it, what will be the answer? In calculator, if you put the values, 16 10 to the power 3, it is 25 ampere, right? So this is 25 ampere. So if I have any doubt, then ask me. This is the part 4. Here you have to calculate the secondary current. When 16 kilowatt at theta 0.8, sorry, it's power factor. So it is cos theta is 0.8. You have to calculate IS. Okay. So you can calculate it more easily because you already calculated IP. So you can easily calculate the IS given 2 minutes. Kritish, I didn't understand what you are saying. Can you explain it?
हेलो सर।
Yes, yes, you can say.
सर, मैं बोल रहा था कि हम अगर P इक्वल टू वी आई कॉस थीटा फॉर्मूला अप्लाई करके हम सेकेंडरी करंट निकाल दे, फिर टर्न्स रेशियो को यूज करके हम प्राइमरी करंट भी निकाल सकते हैं।
हाँ हाँ, जरूर निकाल सकते हैं।
सर हाँ, मैंने वो मेथड फॉलो किया है तो।
या अब मैंने वही फॉलो किया ना।
जी जी
इन
सर।
विच लैंग्वेज यू आर कंफर्टेबल, इंग्लिश, हिंदी है, बंगाली?
सर आई एम इन ओडिया सो।
ओके ओके ओके, आई अंडरस्टैंड इट। सो आई फॉलो दैट formula basically, vi cos theta, right?
जी जी सर।
ठीक है भाई। Fine. So this is very easy. Some of you have get already the answer. So I tell that IT by IS is NS by N. So IS should be IPNP by NS. You can calculate it in this way. This is more easier way. Since you already calculated 25, so 500 by 250 was our trans ratio. So it is 50 ampere. Fine. So in next question section, we have given R naught, XM, RE, XC, all the equivalent parameters of transformer are given, and we have to calculate the LV side current. So here you can see that this is our LV side and this is our HV side. So I already said don't put it in your brain in a conventional way that always this one is HV side. So in this case, this is LV side, this is HV side, and you have to calculate the LV side current. All the parameters are given. Okay. So this will be a complex number solution. So try to solve it. I'm giving 5 minutes for it. Nitish, can you explain it in math? Nitish, you can unmute and say what your query is. Nitish Kumar Jadhav, you said that there was a question in assignment one, that question number 5, I'm not able to unmute. Why I didn't understand? If you didn't able to unmute, I didn't understand what you were saying. If anyone understand what he's saying, he or she can unmute and say.
Hi, sir. Actually, in last section, there is a fifth question. It is there. That is they given two different transformers, but both are having 5 kVA rating. Nitish, am I right? That is the question.
He didn't able to unmute.
Yes, actually, thing is, that question is already solved, sir. I have that answers also with me.
Okay, then it's okay.
Yeah,
It doesn't
we
have any.
actually all the 14 questions what we are having, everything is we discussed actually.
Okay, that doesn't issue.
It's not any
In
issue.
in my class, I always try to solve the assignments questions
Yes,
also.
sir. Yes, yes.
That
All the questions are solved, sir.
then it is more easier for you all to solve the assignment. Will help you all, right?
Yes, sir. Yes, yes. Really. What you tell is really correct.
So if anyone solve it, see here we have all the data like XM and XE, R naught is 140 ohm, right? And anything else given? Hmm. See here the load is missing. So I think for that reason you're not able to solve it. So consider it around 50 plus J30. Okay. So now I think you all able to solve it. So the load is missing, right, in the question. So, so try this. Hello. Yeah, what was the doubt? I didn't understand. Would you please repeat what? Fine. So in this case, you have to calculate the LV current, right? So the load is given as 50 J30, under which you have to solve it. So LV current, what will be current basically? The voltage. So if you are referring this load into the secondary side, then it will be 50 plus J30 into K square, right? K square is here in this case, it will be 100 by 500 square. Since Vp by Vs is Np by Ns. So this is K, right? So current will be the voltage at the primary side, since we are referring the LV side as primary. So the voltage at the LV side, you can also say it like that. The voltage at the LV side is 100, right? So it is 100 by the total impedance. So the total impedance is Re plus R naught. So it is here in this case, that is this one, right? This is J80, JXE. So this one. We're considering this one, Re plus JXE. So this will be our 0.08 and this one is 0.18, right? 0.18. Okay. Plus our load referring to the secondary side. Fine. So this is a complex number solution. So if we solve it, uh, I solve it already for you all. So it will be around 41.35 and the angle is minus 34.45 degree. Check it whether it is correct. If it is correct, then with the same data, we have to solve another question. Then what will be the LV side power factor? What will be the LV side power factor? Fine. So we calculated it as minus 34.45 degree. Then what will be the power factor? What is power factor? Basically, power factor here, the angle theta is minus 34.45 degree. So power factor is cos theta. So it is cos of minus 34.45 degree. Then what will be the answer? It will be 0.8245. So check these two questions, and after which the next part is we have to calculate the HV terminal voltage. Okay. I'm copying the data for you all. First check this, that it is correct or not. When it is correct, I also solve it. So try to solve it and check that it is correct. Then tell me. So if it is correct, then solve for the HV current. Okay. So HV terminal voltage. Okay. Hello. Try to solve the question. There is a network issue here. This is showing it.
I'm giving the question in the comment section. So there is a network issue here. So try to solve the question and after which I will join.
Hello, hello. Hello. So this one is the question. So let me solve it for you all. So there was a network issue. Is it audible? Yes. You can transfer it anyway. The answer should be correct, right? So here, first you have to calculate the HV side current. To calculate the HV side current here, we have 0.08 plus 0.18, right? And whenever you're transferring it into HV side, so we have load of, this was our LV side current, right? So in case of HV side, it will nothing but it will multiply through the inverse of the this, right? Since we have HV by LV equal to NS by NP, so we can calculate it in this way. If you calculate it, it will be around 8.01 at an angle of 33 degree minus. So now we have to calculate the HV side voltage. HV side voltage. To calculate the HV side voltage, it will be HV side current into the load. So if you multiply it, and here you have an angle, so it will be like 8.01 minus of J 8.01 with an angle of this. So I have to calculate it in this way. So final answer will be, so is it correct? Is it same with you all? The next part is output by load power. Okay. So next part is output by load power. Try to solve it. See, in this case, we have to calculate the output by load power, right? So see, we calculated the HV current as at an angle of how much? Minus 33.52 degree, right? So here we have to calculate the output load power by load power. So it will be, we know that I square, the magnitude of it, the resistance it will give the power. So it will be divided by 50 watt. This is our output load ratio. It will be around 3209 watt. Next question, we have to calculate the efficiency, and we calculated the output as 3209 watt. Now we have to calculate the input, and efficiency means output by input into 100%. So we have to calculate the input power, and then for input power, we have to know the input voltage into the input current into cos theta. That is V input into I input into cos theta. So we calculated all the values. So try to solve it. I'm giving you the data addition if you require. Give 2 minutes to solve it. So fine, in this question, you have to calculate the input power. So if his input voltage is 100, it's given. And we calculated that current where it was around 41.35. So we have to take the magnitude only. So it is 41.35 into the power factor we calculated 0.82 something. So if we multiply it, it will be around 3409.638 watt. So now we have to calculate the efficiency. So it will be 3209 by 3409 point something it will be there. So if you calculate it, it will be around 94%. Right. So moving into the next question, we have a data like HV side is 250 volt by 125 volt transformer connected to 50 hertz step down transformer. So the HV side is from primary side to secondary side, and seeing that the voltage is dropping. So this is a step down transformer. It is excited with the rated voltage. It draws a current of 3 ampere at 0.8. So I have to calculate that under lightly load condition, if the transformer is delivering 14 ampere, then what will be the RMS value of the primary side current? Try to solve it. Yes, what is the doubt? 48 kVA, 60 Hz. Try to see these questions, then I think it will be helpful. Fine. So let me solve you all. I didn't get any answer. So see here, what will be the IP? It draws a current at 3 ampere with a power factor lagging. So it is minus cos inverse of 0.2. Fine. Plus, it draws a current of 14 amp at this. So it will be NP, this is reverse of it. So NS by NP into 14 at an angle of, this is also lagging, so minus cos inverse of 0.85. Fine. So if you solve it, then it is 3 into 0.2 plus 50 into 14 into 0.85 plus J of 3 into sine of minus cos inverse of 0.2 plus 125 by 250 14 into sine of minus cos inverse of 0.85. If you solve it, the calculator is 6.55. Next part is around minus J 6.62. So if you solve it, root over of this one plus this one, and the angle will be tan inverse of this. So this is 9.317, and the angle is tan inverse of x by 6.62 by 6.65. The next part is you have to calculate the primary power factor. So what will be the power factor? Since the angle, power factor angle is tan inverse minus how much was 6.62 by 6.65. So, so what will be the cos theta? This cos of tan inverse. If you solve it, cos of this one. So it is 0.702. Clear? So now moving to the next part. We already discussed that there are two losses in a transformer, that is core loss and copper loss. The copper loss is basically due to the I square R loss, but core loss is composed of two losses. One is hysteresis, another one is eddy current. So the basic fundamental behind the hysteresis loss is that we know that hysteresis is basically a characterization where you can see that the magnetic flux density, how much it is lagging with respect to the magnetic field strength is defined. So if you see in this curve that when the magnetic intensity H is increasing, you can see that the flux density is increasing from 0 to A. Fine. But After a certain time, when it reaches point A, see that the magnetic field intensity now slowly trying to decrease from the path ABC. So if you zoom it, it will be then it is decreasing through ABC. Right? Now it is getting, you see that at this point H is 0. Right? But even if the H is 0, the core has retained some value of B. Seeing that this is the BH curve. So this is B, this is H. So at H equal to 0, you see that there is a certain value of B is there. This is called residual flux. Right? Now, after a certain time, you see that B becomes 0. The residual flux will become 0. But at this point, there is some amount of magnetic field strength present. H is present, but in negative. So this is called coercivity. Now, if the H is again increased in the reverse direction, if the H is increased, then you see that the B is going in the negative direction from EFG, and this loop tries to continue again and again. And this is called hysteresis loop. And in case of the transformer, the core, we have some losses due to this hysteresis loop. The energy loss within this is called hysteresis loss. Okay. See here, in case of some metals, you see that this is a silicon steel, this is hard steel, and this is wrought iron. So these are the three examples where you can see that the hysteresis curves are different, and the hysteresis loss will be within the loss within this curve. So from this, you can see that these are this silicon steel has lesser loss, so we generally prefer this as the core for transformer and rotating electric machine. The hard steel is generally used for making permanent magnet, and wrought irons are generally used for making electromagnets. Now here, if you don't move into these calculations more and more, then you can see that in a simple word, you can say that the hysteresis loss is basically proportional to magnetic flux density, frequency, and the volume of the core. So at a glance, you can say that since Vmax is proportional to V by F, you can say that this hysteresis loss is proportional to V by F into F. Right? It is basically this hysteresis, if Vmax is constant, if this is constant, then we can say that pH is proportional to F. And if this is not constant, then pH is proportional to pH or WH is proportional to V square. These are the two equations we require to solve some problem. When when flux density is constant, then this is constant, then it is proportional to F proportional to V. But when this is not constant, then it is proportional to V and F. Sorry, not V square, proportional to V only, proportional to V. And this one is volume. Okay. Another kind of loss is the eddy current loss. This is another power loss that happens in transformer also. This is whenever there is a current flowing in closed path, there will be some kind of losses appears in transformer. This is due to eddy current loss. This is also proportional to B square Fs square. You can see that. And here also, if B is constant, then our eddy current loss, this eddy current loss is proportional to Fs square. If B is constant. If it is not constant, then P is proportional to V square. Why? Since it can be replaced as V square by Fs square into Fs square, it will cut out and it is proportional to V square. So try to keep in mind that when B is constant, what will be the proportionality? When B is not constant, what will be the proportionality? Based on which we have to solve the problem. So this is the first question. So where we are given the hysteresis loss 780 watt, eddy current loss 380 watt, and Steinmetz constant is 1.6. We have to calculate it. Hysteresis loss at, for this question, you have to calculate it hysteresis loss when it is operating as 300 volt 50 hertz. First, it was working at a V1 of 440 volt, F1 60 hertz. Now the V2 becomes 300, F2 becomes 50. Okay. So pH1, pH2, try to solve in this way. Given 2 minutes. See, in this case, what will happen? See, this one is proportional to V1 by V2 to the power Steinmetz constant into F1 by F2 to the power Steinmetz constant. So we have all the values, and We have the values of pH2 also. So pH1 equal to 780 watt into, so if you solve it, what will be the answer? It will be around 471.49 watt. This question has another part, that is, in similar way, we have to calculate the, in similar way, we have to calculate the eddy current loss. In case of eddy current loss, we know that P1 by P2 should be proportional to phi1 max square. So P1 is equal to P2 into phi1 phi2. That is basically V1 by V2 square. Right? So ultimately, see, this will be V1 by F1 square by V2 by F2 square into F1 square by F2 square. So ultimately, F1 F2 square cut out. It will be P2 into V1 by V2 square. It is P2, the value of P2 is 380 watt. So now it is 380 into, firstly the voltage was 440, right? So it is 300 by 440. So ultimately the answer is 176.65 watt. So you have to solve the questions like this. Okay. Now, this is basically a transformer. I already discussed in class 1 that this is a transformer having input side current I1 and primary turns in N1, N2, and this is E1, E2. Right? So if we assume that we are giving an AC current, AC voltage here, then the magnetic flux produced here is phi m sine omega. Okay. Now the EMF generated according to the Faraday's law, it will be N d phi dt. So EMF at primary will be N d phi dt. The phi is phi m sine omega t. So if we differentiate it, it will be minus N1 omega cos omega t. See, sine omega t. If we differentiate it, it will be omega of cos omega t. Right? We got E1 as minus 2 pi n phi m cos omega t. Okay. So the RMS value, so if you take the maximum value of it, then it will be EM1 sine omega t minus N90. So this is 2 pi n phi m. So the RMS value will be the maximum by root 2. So this is, finally we are getting 4.44 pi Fn1 as our primary side RMS EMF, and for secondary side it will be similar frequency into phi F into N2. In some book, the phi can be referred as B. In some book, whenever B is referred as phi, that is phi by F. So B is proportional to phi F. C. So at a general, we can say that the EMF of a transformer is basically 4.44 into F into phi into F. So if you have to calculate the EMF of a transformer, you have to calculate by this formula. So based on which I am giving a problem, the calculated flux, where we have, it is taking a current of 4.5 ampere at a power factor of 0.35. Primary time turns are NP equal to 200. Vp, Vs are given. Frequency is 50 Hz. The current drawing is 4.5 amps. So rated flux. What will be the rated flux? So based on this formula, you have to calculate. Okay. So this is the last set of questions I'm giving you. Yeah, it is correct. You can solve the next part, the magnetizing component. Here you have to calculate the IM. Okay, so basically IM is the no load current into sine theta. You have to calculate theta, that is cos inverse of 0.35, which is given. Okay, so now we can solve it. So Vijayalakshmi, is it correct? So it is 4.5 into sine of cos inverse of 0.3. So what will be the answer? It is around 4.2. Right? Another part, this is the last part, we have to calculate the rated core or iron loss. So basically, this is Vp into I naught into cos phi. Right. So cos phi is given as 0.35, Vp is 500, and this is 4.5. So if we calculate it, what will be the answer? So to solve it, will be around 787.5 watt. Clear? Is it clear? If you have any doubt, you can ask, or I can drop it. If you have any doubt, you can ask it. Otherwise, it's over. You're fine. So if you don't have any doubt, so good
Sir,
night. Yes.
sir, question number 14. Estimate eddy current loss.
Yeah, let me see.
Sir, in that V1 by V2 whole square, sir.
Yes,
Actually, V1
yes.
is given as 440, V2 is 300.
No, it is reverse. It is,
Okay, sir.
we have to calculate V2, sorry, VP1, right?
Okay, sir. Yes, sir.
So it will be V2 by V1 square, right?
Yes, sir. Yes, sir.
Okay. Okay. Is it
Thank you, sir.
clear?
Yes, sir. Yes, sir.
Okay. Everything is clear? Okay. And good night. All the best. Try to solve the assignments properly. Okay.